You've got up in the top right-hand corner 30% of deaths toxic, kinetic, microbial, genetic. But down in this giant 70% of all deaths, you've got chronic disease. And of course, the big three, cancer, cardiovascular disease, and chronic neurodegenerative diseases like Alzheimer's. What we know about all this chronic disease is that it's driven by sedimentation and malnutrition. This is poor diet and lack of exercise. And underpinning all of this stuff is insulin resistance. And that is why this is such a huge, big topic. I use HOMA-IR a lot in my patients these days. This is homeostatic model assessment of insulin resistance. This is my favorite way to non-invasively measure insulin resistance in my patients. This is something you'll see most commonly in the medical literature when people are looking at insulin resistance. It's really just your fasting glucose times your fasting insulin divided by 405. And it's answering the question, how much insulin does it take when I'm fasting to hold my blood sugar and my fat stores where they're at right now? Average in this country is 1.75. That's really a little too high. You want to be at 1.0 or lower. Anything over about 2.5 is clearly insulin resistance. You could just search the medical literature for HOMA-IR and any chronic disease you can think of, and it's just a huge linear association. HOMA-IR and cardiovascular disease, huge linear association. Dying of heart attacks, huge association. Cancer, huge association. All forms of cancer, huge association. I mean, it's just ridiculous. Alzheimer's pathology, massive association with insulin resistance. And finally, just dying. All-cause mortality and HOMA-IR, big association there too. So this is a really important topic. Okay, so now what causes insulin resistance? Well, we've known forever that the more abdominal fat you have, the more insulin resistant you are. This graph on the right shows insulin levels. You've got normal in green, obese in yellow, and abdominal obesity in red. So we've known that for a long time. But what about this? Here's a graph of insulin sensitivity versus body mass index. And how do you explain these people way down here? They've got a BMI less than 20, but their insulin sensitivity is terrible. I mean, what's going on here, right? Well, we've known for over 50 years that the larger your adipocytes, the more insulin resistant you are, right? And in fact, it's a perfectly linear association. Your adipocytes can expand in diameter about 20 times. So if you look at a cross-section of adipocytes under a microscope, they can go from maybe 10, 20 microns to 200 microns. That means their volume can expand by 8,000 times. And as they get bigger, they get more insulin resistant. And it's very, very linear. It turns out that large adipocytes are resistant to the anti-lipolytic effects of insulin, and it's harder to shove more fat in there, right? You can graph out fasting insulin, HOMA-IR, any marker of metabolic syndrome, it's perfectly linear with adipocyte size. Triglycerides go up, HDL goes down, HOMA-IR goes up, insulin goes up. Any metabolic syndrome or insulin resistance marker you measure will completely correlate up or down linearly with the size of your adipocytes. If you have gastric bypass surgery and you manage to shrink the size of your adipocytes, you'll reverse insulin resistance and diabetes. If you lose weight with any mechanism, it's more important how much you shrink your adipocytes rather than how much weight you actually lose in terms of reversing insulin resistance. And that's why people can reverse insulin resistance really rapidly even before they lose a whole lot of weight. It turns out that as you get fatter, your fat cells can do one of two things. You can have adipocyte hypertrophy, and that's where your fat cell gets overstuffed with fat. And it's inflamed and it's insulin resistant and it doesn't want any more fat or glucose. Or you can have adipocyte hyperplasia. If you have the right genetics, you can sprout cute new little baby fat cells that are very insulin sensitive and they're happy to suck up more fat and they're not inflamed and they're not insulin resistant. So not all your fat cells are alike, right? Your ginormous, huge, overstuffed fat cells are super inflamed, they're sick, they're dying, they're spewing out fat constantly. It takes a crap ton of insulin to shove fat in there. The fat doesn't want to stay in there. But your cute little baby fat cells are very insulin sensitive and they're more than happy to suck up more fat flux, right? So you can have two people of identical obesity. And the person who's overstuffed their fat cells and had adipocyte hypertrophy is going to be inflamed and insulin resistant And it takes a ton of insulin to shove any more fat in there, and the fat is constantly spewing back out. But somebody who can sprout new little baby fat cells is going to stay insulin sensitive forever. If you have the right genetics and you can just sprout new fat cells, this hyperplasia, you could be 600 pounds, and as long as you have some small fat cells around to still suck up more fat, you're going to be totally insulin sensitive. This is about 10% of obese people. Fat is typically stored in the subcutaneous first, and then it spills over into visceral, and then it spills over into liver and muscle and pancreas and blood vessels, and you've got ectopic fat, and you have fat everywhere, and then you're horribly insulin resistant. Here's a sort of a schematic of how it works. You fill up your subcutaneous adipose first, it spills over into visceral, that spills over into liver and muscle, and now you've got ectopic fat, and none of your tissues want any fat or glucose, and now you're insulin resistant. My favorite term when it comes to this concept is personal fat threshold. PFT, this is a genetic limit to how fat you can get before you just can't get fatter and you're insulin resistant. This explains people who are TOFI, thin on the outside, fat on the inside. These are people who look thin, but they've completely maxed out their fat source, subcutaneous and visceral, and they're horribly insulin resistant or maybe completely diabetic. This is why China and India have passed up diabetes prevalence compared to the US at a much lower body mass index, right? Personal fat threshold. I love this graph right here. It takes a ton of insulin to shove that much fat into an adipocyte and hold it there and to pin it there tonically. And that fat is constantly trying to spew back out. And that's why people who've maxed out their fat cells just have high insulin 24/7. This is a beautiful illustration. Okay, the best example we have of adipose tissue controlling insulin resistance is lipodystrophy. Lipodystrophy is a series of disorders where you don't have any subcutaneous fat, or hardly any. I have a bunch of patients with lipodystrophy. They're very unique. They almost look ripped like a bodybuilder. They have very defined arms and legs. They have very little subcutaneous fat, but they have a lot more visceral fat than you would expect. If you do cross-sectional imaging on these people, the subcu fat in red here is very, very small, but the visceral fat is completely maxed out. And almost everyone with lipodystrophy has horrible insulin resistance and horrible brittle diabetes. All of my lipodystrophy patients really bad diabetes. So here's how it works so far, right? You fill up your subcutaneous fat, then it spills over into visceral, that spills over into liver and muscle. Now you've got ectopic fat, you've got fat everywhere, none of your cells want fat, none of your tissues want fat, you're insulin resistant. What's really going on here is your body is at war with itself, right? None of your cells want fat, none of your tissues want fat, none of them want glucose either, none of them want any of this energy, and it's like this horrible game of musical chairs where insulin just gets louder and louder and louder until you finally shove some fat or glucose into whatever cell or tissue is the least insulin resistant, and next time it'll probably be even more insulin resistant. Game of musical chairs where insulin just gets louder and louder and louder until you finally shove some fat or glucose into whatever cell or tissue is the least insulin resistant, and next time it'll probably be even more insulin resistant. And once your body is at war with itself like this, the wheels just fall off your wagon, and this is why all of these chronic diseases are driven by insulin resistance. Okay, bottom line so far. You're insulin resistant because you filled up all your adipocytes, right? You have no more room for fat flux. Every time you eat a meal, it has nowhere to go, the fat or the glucose. So you're just completely filled, and that's why you're insulin resistant, and that's why you're hyperinsulinemic, and you have high insulin all the time. But this is just the beginning. I mean, the big question is, why did you fill up your adipocytes, right? Why are they all full? Is it because humans shouldn't eat fat because we should be low-fat vegans? Is it because you're just a glutton and you eat too much, right? No. You filled up your fat cells with fat because you suck at burning fat because you eat too much glucose. An important contributing factor for obesity is reduced fat oxidation and increased metabolism of carbohydrate. This has been brought about by a shift towards the body's preference towards oxidizing carbohydrate rather than fat, resulting in increased deposition of body fat. You're eating carbs and glucose, you're not burning fat, it accumulates, you fill up your adipose. Turns out, everybody with obesity, insulin resistance, ectopic fat has defects in mitochondrial metabolism of fat. Everyone in this situation has trouble metabolizing fat in their mitochondria. Mitochondrial mass, structure, function are altered in insulin resistance. Defects of mitochondria are believed to contribute to impaired fat oxidation and to the accumulation of intracellular lipid intermediates, which contribute to the pathogenesis of insulin resistance. Mitochondrial dysfunction in the elderly and in the offspring of diabetic patients is well documented. So basically, you're not burning fat well, it accumulates, you fill up your adipose. Now, only your mitochondria can oxidize fat, right? It's all happening in the mitochondria. And let's talk about them for a second. Every nucleated cell in your body has mitochondria in it, right? And they're just constantly turning your food into ATP, which drives everything in your body. And the turnover rate is just enormous. Every single day you make your entire body mass in ATP molecules. If you're a 70-kilogram male, you manufacture 70 kilograms of ATP molecules every day, which is ridiculous. The turnover is so fast that at any given second in time, you only have 6 seconds of ATP left in your body. Or, in fact, that is what cyanide does. Cyanide poisons your electron transport chain, and you can't make ATP and you're dead 6 seconds later. So these suckers are constantly performing metabolism. And there are 3 things going into the cell that your mitochondria can burn. Glucose, FFAs, free fatty acids, that's just fat, or amino acids. Now, amino acids is sort of a minor player. Most of the time, people are oxidizing glucose or fat. And glucose and fat are oxidized reciprocally. So anytime you're burning more glucose, you're burning less fat, and more fat, you're burning less glucose, right? Now you can actually tell what the fuel mixture is in every mitochondria in every cell of your body by measuring a respiratory quotient, right? You actually breathe out a lot more carbon dioxide if you're burning glucose in your mitochondria than if you're burning fat. You breathe out less carbon dioxide. And because they're reciprocal, you can actually calculate it out. If you have the highest respiratory quotient of 1.0, you're breathing out the most carbon dioxide and you're burning pure glucose in all your cells, all your mitochondria. If you have the lowest respiratory quotient of 0.7, you're burning pure fat and you're making the least carbon dioxide. And because it's reciprocal, you can just look at that line and tell exactly what your fuel mixture is based on your respiratory quotient. The fascinating thing about respiratory quotient is you could take 2 people in this room and measure their baseline respiratory quotient. And whoever has the higher one, meaning they're burning more glucose and less fat at baseline, will literally be significantly fatter 3 years down the road. That's what this study was. Measure baseline RQ, whoever's burning more glucose and less fat is literally going to be fatter later. Defective fat oxidation remains the likely explanation for this finding. Yeah, I couldn't agree more. It turns out you can take 2 people of the same obesity, whoever has the lower respiratory quotient, meaning they're burning more fat, is going to be metabolically healthier. They're going to have lower insulin, less metabolic syndrome. There's also this concept of metabolic flexibility. Metabolic flexibility is the ability to drop your RQ if you're eating more fat. So if I'm thin and healthy and I have tons of really good mitochondria and I'm good at burning fat, if I eat a high-fat diet, I will immediately drop my RQ and burn more fat. Also, if I'm fasting and I'm just living off of fat, my RQ goes way down. People with poor metabolic flexibility can't do that. If they eat a higher fat diet, they end up just storing that. If they are fasting, they struggle to meet their metabolic needs just from fat. Now, okay, this is a really important point. If you're on a mixed diet, and you eat a bunch more carbs, you will immediately raise your RQ in anybody. You can drive up anyone's RQ by feeding them more carbs and glucose because glucose completely controls metabolism and substrate oxidation. It has to, because you don't have anywhere for that glucose to go. So if I feed anyone more carbs, their RQ goes up. The same isn't true on a mixed diet. If you're eating just a regular standard American diet and you add more fat to it, you just throw a stick of butter on top, you will not drop your RQ. You will just store all of that butter. I'm reading in this box here, excess carbohydrate results in increased carbohydrate oxidation, a lower fat oxidation, increased RQ. This is not the case for fat. Excess fat intake on a mixed diet does not stimulate fat oxidation, but enhances fat storage. That's because glucose, rather than fat, completely controls substrate oxidation, right? Glucose controls oxidation. You only have a tiny little carb glucose reservoir. It's really small. You know, you can have, what, 5 grams of glucose in your bloodstream, maybe a couple hundred grams in your liver and your muscle, and that's it. So when you dump in a bunch of carbs and glucose, you literally have to switch your metabolism over and burn more glucose. I've made a fancier little hydraulic model of metabolism here. And again, you've got a fat reservoir on the right, so when you dump more fat in, nothing has to change. But as you add carbohydrates and raise glucose, you literally have to switch your metabolism over and burn more glucose just to get rid of it. You just have no other choice. That's how it has to work. In fact, if you eat enough carbohydrates and glucose, you literally have to convert it to fat via de novo lipogenesis to store it and get rid of it. Only when carbohydrates and glucose are absent can you switch your fuel mixture over and burn fat again. If you're good at burning fat, you have epigenetic changes that upregulate your fat-burning pathways, and you'll stay good at burning fat for a period of time. It's like an inertia or a memory to your metabolism. On the other hand, if you're a glucose burner, you have epigenetic changes, you upregulate glucose burning, and you sort of stay good at that. That's why it takes 1 to 3 weeks to switch over from a high-carb diet to a low-carb diet. Okay, this study sums it up so well, I'm just going to quote directly from it. The development of insulin resistance is the impaired ability of skeletal muscle to oxidize fatty acids as a consequence of elevated glucose oxidation in the situation of hyperglycemia and hyperinsulinemia, and the impaired ability to switch easily between glucose and fat oxidation in response to homeostatic signals. The decreased fat oxidation results in the accumulation of intermediates of fatty acid metabolism. Basically, there's so much carbs and glucose around, you can't burn fat, the fat accumulates, now you're insulin resistant. This concept of metabolic flexibility goes all the way down to the mitochondrial level. So here's your mitochondria with the two inputs, glucose and fat. And a healthy mitochondria can easily flex back and forth, glucose, fat, glucose, fat. But if you have an inflexible mitochondria, one of these damaged mitochondria, it's really bad at doing that. It really struggles. What's going on inside your mitochondria is you've got glucose and long-chain fatty acids, the two input into the cell, right? Glucose and fat. Glucose goes into the mitochondria, and when you dump in a bunch of extra glucose, you have increased citrate, and citrate gets exported to the cell. And because there's extra citrate, your body knows it's time to make fat instead of burning fat. So your cell's going to make fat. It converts it into malonyl-CoA. That literally blocks carnitine palmitoyltransferase 1, CPT1, and fat actually physically cannot enter your mitochondria to be burned when malonyl-CoA is elevated. In other words, when you're making fat, you don't want to burn fat. That would be wasteful. So all your fat gets rerouted as triglycerides to be stored. Here's another illustration of the same thing. You dump in a bunch of glucose, you export citrate, malonyl-CoA, first committed step to making fat. So you don't want to burn fat, and you block entry of fat into the mitochondria, and all your fat accumulates as triglycerides to be exported and stored. What's really going on here is your body is way too efficient to make fat and burn fat at the same time. So when you dump a bunch of glucose into your cell, your body knows it's going to make fat, right? Fatty acid synthesis. And malonyl-CoA, as the first committed step to fatty acid synthesis, blocks CPT1. Because you don't want to be making fat on one side here on the right and then burning fat on the other side. That would be a futile cycle, right? That your body's not going to do that. That's why glucose and fat are burned reciprocally all the way down at your mitochondrial level. Because when you're burning glucose and you're going to be making fat, you don't want to be burning fat. We've proven that this happens. Here's a brilliant study that literally proves this. They measured oxidation of glucose and fat in the mitochondria. At baseline, they infused people with glucose and insulin, and bam, immediately glucose oxidation goes way up, fat oxidation goes way down. This is just how it works. This is why if you eat carbs all day long, you're not burning any fat at all. Rather, the intracellular availability of glucose, not fatty acids, is the prime determinant of the substrate mix, i.e. glucose versus fat, that is oxidized for energy. In other words, you dump in glucose, you literally have to burn glucose, not fat. That's just how the whole system works. Here's a cuter picture of it, right? Insulin binds to the cell. Up in the upper left-hand corner, the GLUT4 transporter goes to the surface, glucose comes in, it's converted to malonyl-CoA because you're going to turn it into fat, so that blocks CPT1 so you don't burn any fat. And then all your fat accumulates there in yellow. And in fact, what happens is your cell sees what's going on here, all this fat is accumulating, and the accumulated fat shuts off insulin signaling. So the GLUT4 transporter goes back inside the cell, and your cell's refusing glucose, right? Your cell doesn't want any more glucose. Look at all this fat that accumulated. Your cell doesn't want glucose, right? Your cell is smarter than you are. What could you do with your diet when your cell doesn't want more glucose? I can't think of anything, but that's probably something. Now, if we take it even one layer deeper and look at the electron transport chain, you're pumping all these protons across this membrane. It's like a little battery that powers your ATP synthase motor, and it spring loads all your ATP molecules. When you're just doing beta oxidation of fat, everything runs really smoothly. You're level loading your electron transport chain. The membrane potential is perfect. Everything's nice. Your body's designed to just live off of stored body fat. So just burning fat has to work perfectly. But you dump a bunch of glucose on top of this, and you overdrive complex 1, and you get too much membrane potential and too many reactive oxygen species, and you literally get something called glucose toxicity in your mitochondria. You can basically bust those suckers by trying to burn sugar on top of beta oxidation. Okay, let's take this into the real world, right? Real world. Here's a company that specializes in obesogenic rat chow. This is what they do. They make an obesogenic rat chow that people pay money for this stuff. It's supposed to make you as fat as possible, as fast as possible. I'm talking visceral obesity, liver fat, insulin resistance, diabetes, the whole thing. This obesogenic rat chow is very low in protein. It's really high in carbs if you look at the grams. It's vaguely, eerily similar to the standard American diets, which is pretty sad, right? Yeah. So we know how to make both animals and humans as fat as possible, as rapidly as possible. It's sugar and fat together, right? The obesogenic rat chow is a refined, processed, concentrated fat and sugar mixed together. It's usually cornstarch and vegetable oil or something like that. But it's low in protein, low in nutrients. It's just sugar and fat. And that is how you get anything as fat as possible, as rapidly as possible. You can feed humans donuts. It's pretty much the same thing. So we know how to get the very highest insulin levels, the most overfilled adipocytes, the worst body composition, the highest fat mass, the lowest lean mass. You do that by feeding high carb and high fat, right? And you keep everything else low. Sugar and fat, this is the absolute worst. We also know how to get your adipocytes the very smallest and how to get the very lowest insulin levels. And we know that thanks to natural bodybuilders and fitness models. We have studies that document how this is done. This is female fitness competitors. They achieve this low body fat, reducing carbohydrate intake while maintaining a high level of protein, resistance training, and moderate fat. So it's basically very low carb, high protein, moderate fat, and lifting. So we also know what calories got dumped into the American diet to cause the obesity epidemic over the past 60 years, right? Grains, oils, and sugars. This is flour, sugar, and oil. Or as I call it, the processed food trifecta, right? Flour, sugar, and oil. In 2010, 60% of all the American calories were flour, sugar, and oil. We're literally eating obesogenic rat chow, and we're just maxing out all our fat cells, right? I just want to point out that your adipocytes are there for daily fat flux. Your adipocytes are supposed to expand during the day when you're eating, shrink at night when you're fasting and living off of stored fat. And as long as you have plenty of room for fat flux, as long as your adipocytes are empty enough that you have plenty of room for this flux, everything's fine. That's how it's supposed to work. There's also a seasonal component to this fat flux piece. All energy on Earth comes from the sun. In the summertime, there's more sunlight. Plants make more sugar. Herbivores eat more sugar and they get fatter. Carnivores eat more fat from fatter herbivores and they get fatter. Omnivores, like humans, come along. We eat more sugar and more fat and we get really fatter. The classic example is a bear, right? This is a classic omnivore. And these are actual bear adipocytes. In the summer, they've got sugar. They eat fruit and honey and berries. And then in the winter time, everything changes, right? No more glucose at all. There's no plant sugars at all in the winter time. So they're just eating protein and fat. I just want to end by saying that in this country, we've made it summertime, the peak of summertime, 24 hours a day, 365 days a year. It's just sugar and fat together, day after day after day. We've all maxed out our adipocytes. Half the planet's insulin resistant. And I think it's time a lot of us made it autumn. where there's a lot less plant sugars and way less glucose. So we can finally burn some fat for a change.